In this video, we will present some of our recent work on robust trajectory optimization for robot locomotion in the presence of uncertainty in the terrain model. Incorporating robustness to terrain uncertainty into motion planning could greatly benefit the development of safe legged locomotion strategies for robots. As Spot demonstrates, unmodeled disturbances from the terrain, such as abrupt changes in friction due to banana peels, can cause robots to slip and fall. And while Spot can eventually get back up, methods for planning robust locomotion strategies are needed to avoid falling altogether. One common method for planning robot motion over terrain is contact implicit trajectory optimization. In this method, contact with the terrain is modeled through complementarity constraints on the states and ground reaction forces in an optimal control problem. Because the constraints encode a precise terrain model, the solutions are sensitive to errors and uncertainty. In our approach, we specifically model uncertainty in the terrain model. We assume that the terrain parameters, such as the normal distance to the terrain and the friction coefficient, are normally distributed. We replace the complementarity constraints with a residual function psi, and then minimize the expected residual under the associated terrain distribution in a method called expected residual minimization. Then we add the expected residual to our optimization cost function in a weighted sum and solve the resulting trajectory optimization problem. Throughout our work, we compare the results from our ERM approach to those generated using the traditional contact implicit approach with the expected values of the terrain parameters. We tested our ERM approach in 3 examples: sliding a block over terrain with an uncertain friction coefficient, propelling a cart forward by making contact with the ground at an uncertain terrain height, and finally a hopper traversing terrain with an uncertain terrain height and an uncertain friction coefficient. In our first example, we must slide a block over terrain where the friction coefficient is uncertain. We first compare trajectories generated with the ERM cost for uncertain friction to those generated without the cost. Then we evaluate the performance of the optimized controls in open-loop simulations with disturbances in the friction coefficient. We assumed the friction coefficient had an expected value of 0.5 and a standard deviation of 0.1. Comparing the ERM and non-ERM trajectories, we found that the ERM cost increases the sliding velocity and reduces the sliding time, but maintains the same friction force during sliding as the reference optimization, which used the expected value of the friction coefficient. By varying the uncertainty, we found that the trajectories produced by the ERM cost converge to the reference trajectory as the friction coefficient becomes more certain. We found that this convergence applies not only to the position trajectory of the block, but also to the optimized state, control, and reaction force trajectories. To evaluate the robustness of our method, we simulated the controls produced by the ERM and by a reference trajectory optimization over terrains with different friction coefficients. We also benchmarked the performance against controls produced by a worst-case robust scenario optimization. When the friction coefficient is higher than expected, we found that the controls undershot the goal position, with the ERM controls achieving the closest final position to the goal. When the friction coefficient is lower than expected, the worst-case control simulation achieves the goal position, while the ERM and reference control simulations overshot the goal. By comparing the simulated position traces across a range of friction coefficients, we see that the reference and worst-case simulations have a similar spread in final position, but that the ERM control generates trajectories with a tighter spread around the desired position, indicating the ERM controls are more robust to friction variations. In our second example, a cart is constrained on a horizontal frictionless track and must propel itself using a two-link pendulum to contact the ground. Here we assume the error in the distance to the terrain has 0 mean and a standard deviation of 1 meter. We compared the ERM-generated trajectories to a non-ERM reference and found that the ERM attempts to increase the distance between the end effector contact point and the terrain. As with the sliding block, we also tested the effects of the ERM cost with different levels of uncertainty in the terrain height. We found that the foot height increases with increasing uncertainty, and that as the uncertainty decreases, the ERM-generated trajectories converge to the non-ERM reference trajectory. In our final example, we combine uncertainty in the friction coefficient and in the terrain height in a single leg hopping example with contact points at both the toe and the heel. As with the previous examples, we compared ERM-generated trajectories to reference trajectories and found that the ERM produces higher hopping than the non-robust trajectory. However, the ERM also permits some force at a distance from the expected value of the terrain, while the non-ERM trajectory does not. Unlike in the cart example, the hopper base is free to move in the vertical direction. To better understand the effects of the ERM cost, we again tested several values of the terrain height uncertainty. As before, we found that the ERM trajectories produced higher foot clearance with increasing terrain height uncertainty. However, even though the base height is free, the ERM cost does not increase the base height during hopping by a similar amount. In summary, we have tested the effects of including an ERM cost to model uncertainty in the terrain parameters into trajectory optimization. We found that the ERM produces behaviors which are contact averse. Costs encoding friction coefficient uncertainty reduce sliding time to avoid friction forces, and costs encoding height uncertainty increase the contact distance to avoid the terrain. As the uncertainty decreases, however, the ERM trajectories converge to the optimal trajectories generated under traditional methods. We believe our study marks an important first step towards reasoning about robustness to uncertainty in the terrain during motion planning. Future works may focus on producing contact-seeking behaviors by including a reward for contact interaction, or on updating the terrain model and uncertainty information from locomotion data.